Chemistry, the Central Science, Chapter 8, Basic Concepts of Chemical Bonding, Lesson 2. So how do we draw Lewis structures? We talked about it briefly in the first lesson here. So what are we looking at? We're looking at how many valence electrons does each atom bring to the table. We identify our central atom by it's either the only one that's there, or it's the one that can make the most number of bonds, and sometimes it's going to be the least electronegative atom. So one of these things is going to lead you in the right direction to figuring out which atom goes in the middle. Each atom then that surrounds the central atom has to be connected at least one time. So you draw your single line from the central atom to all the surrounding atoms. After you've done that, you go in and fill octets for all atoms that have to have an octet by placing lone pairs of electrons around those atoms. And we always put them on the most electronegative atom first because they would be the ones that would want the electrons more anyways. Then you go in and you look to see, does everything have 8 electrons that should? Are we making sure we're not double bonding hydrogen, because that can never happen? And are we making sure that we don't have too many electrons there, right? So you do your total electron count, and then you compare again. If you have too many electrons, then you're going to have to erase a pair. And then that's actually going to tell you that you need to form a multiple bond. So be very hesitant at first to just start double bonding and triple bonding things, because more often than not, you'll end up with crazy looking structures that will not be correct. So nitrogen trifluoride says NF3, right? N is less electronegative than fluorine, so we put it in the center. Nitrogen brings 5 electrons. Each fluorine atom brings 7, so our total is going to be 26 electrons. And we're going to form our single bonds between nitrogen and fluorine. Then we go in and complete our octets, right? So right now, each fluorine is going to take 3 lone pairs, and then our nitrogen is going to end up with a lone pair, such that we have a total count there because nitrogen has 3 bonds, which counts for 6 electrons, plus the lone pair is 8. And then each fluorine atom has 3 lone pairs and 1 bond, which also adds up to 8 electrons total. So here we have our shape, which is actually trigonal pyramidal. We'll learn about that in the next chapter, showing us nitrogen trifluoride. Do we have the correct number of valence electrons? If we do our electron count and we go through fluorine with its 6 dots and single line, each of those is 8. So 8 times 3 is 24, plus the 2 dots on nitrogen gives us 26. How about for the carbonate ion? So we keep in mind carbonate is CO3 with a -2 charge. Carbon is less electronegative, and it can form more bonds than oxygen can, so we put carbon in the center. We're going to form our single bonds first, right? After we count up our electrons, keeping in mind that the -2 charge says that we have to add an extra 2 electrons in. Carbon has 4 valence electrons. Oxygen has 6. There are 3 oxygens, so that's 18 plus 4 plus 2, which totals up to 24 electrons. So we draw our single bonds, and then we put dots on everything. Is everything satisfied? Well, each atom here is shown to have 8 electrons. However, if we go in and do our electron count, we would see that we actually have too many electrons, right? This would be 26 electrons, so we'd have to erase a pair off of the carbon atom, and then we're going to form a double bond. So that is what the carbonate ion would look like. And we know that, there are 20. And we know that with this, we can form a double bond between any one of those oxygens. So it can be the one to the right, the one down, or the one to the left, which then leads us into the fact that the carbonate ion has resonance structures. So in terms of formal charge, if we look at formaldehyde, what are 2 possible skeletal structures, right? Just your basic backbone of CH2O. We know hydrogens can't be in the middle. We expect carbon to be somewhere in the middle because it can form the most bonds. So we expect carbon to be connected to oxygen. So is it the structure on the left or the structure on the right? When we're looking at formal charges, we're looking at how many valence electrons does an atom start with, and then how many electrons are associated with it. All the atom's non-bonding electrons are associated with it, i.e. lone pairs, and then half of the atom's bonding electrons are associated with the atom, i.e. the lines, right? So if you look at your number of valence electrons that you start with, you subtract the number of lines and you subtract the number of dots associated with that atom, you get your formal charge. Your formal charge always has to add up to the charge on the molecule or ion that's present. So in this instance, formaldehyde is neutral, so your formal charges have to add up to 0. When we look at Lewis structures, we want to have a structure that has the fewest number of formal charges. So we want to have everything have a formal charge of 0, or we want to have something maybe with a -1 and a +1. But to get into higher charges like -2, -3, or +2 or +3, that's going to lead to instability in the molecule. So here's a possibility for the formaldehyde structure. We're showing each hydrogen has 2 electrons that are, right, that if we formed a bond. Carbon and oxygen both have 8 electrons. And we aren't breaking any rules here because we're starting with 12 electrons because carbon brings 4, oxygen brings 6, and each hydrogen brings 1. So if we count them all up, we end up with 12. We started with 12, so we're good. When we look at when we look at calculating formal charges, we'll see that hydrogen has a formal charge of 0, but what about our carbon and oxygen? So carbon starts with 4. We can see that we're subtracting out the 3 lines and the 2 dots. That would give carbon a charge of -1, right? Because 4 minus 2 minus half of 6, which are the 3 lines, is -1. On oxygen, we end up with a formal charge of starting with 6 valence electrons. We subtract out the 2 dots, and we subtract out the 3 lines, or half times 6. And that gives us a charge of +1. So we have a valid structure here for formaldehyde, where carbon has a -1 formal charge and oxygen has a +1 formal charge. These are different than oxidation numbers. So what about the other structure here? If we have both hydrogens coming off of carbon and we double bond the oxygen, carbon still has its 8 electrons, oxygen still has its 8 electrons, hydrogen is making its single bond like it does. So 12 to start, 12 to finish. So now we can once again look at calculating our formal charges. I look at carbon. I know carbon starts with 4. It has no lone pairs, and it has 4 bonds, which is a total of 8 electrons, right? Half of 8 is 4. So we end up with a formal charge of 0 on carbon. We can do the same thing for oxygen. Starts with 6 valence electrons. We subtract out the 4 dots, right, from the 2 lone pairs, and then we subtract the 2 lines, or half of 4, because there's 2 electrons per line, and that's going to give us a formal charge of 0. So which is our better structure? Well, this one here is that has the double bond oxygen, and this is indeed the actual structure for formaldehyde. So as I stated earlier, neutral molecules, a Lewis structure where there are no formal charges, is preferable. And where we have Lewis structures that have a negative charge overall, you want to have your negative charges on your more electronegative atoms. And we want as small formal charge as possible, right? So, and if you have a more electropositive atom, then you want the positive charge, if you have to have one, to be placed on the more electropositive atom. So comparing those, like I said, your most likely structure for formaldehyde then is the one on the right, and that is the true structure. So I spoke briefly about resonance, and resonance is when you're looking at the fact that you have lone pairs of electrons or double bonds or triple bonds that can be moved around the structure. So you're not changing your basic skeletal structure, which means you have the same single bonds from each structure that you write out. The only thing that is different is where a double bond might be placed, or a triple bond might be placed, or a lone pair of electrons. So you can't just change the overall structure. So here's ozone, and we notice comparing the structure on the left to the structure on the right. Right, the left one, we've got the double bond on the left oxygen. The right one, we've got the double bond on the right. But we can see that all we've done is moved around lone pairs and the double bonds. The central atom has not changed at all. And the central oxygen atom has a formal charge of +1. And the oxygen that is a single bond with 3 lone pairs in either structure has a charge of -1. So here, these structures are effectively equivalent, right? And what we would see because of this resonance is that there isn't a true double bond or single bond between any of these oxygen atoms. It is somewhere in between, right? So if we measured the bond length or we measured the bond enthalpy here, it would not be a true bond distance of a single bond oxygen or a true distance of a double bond oxygen, nor the enthalpy associated with those. It would be somewhere in between. And so these electrons are kind of shared throughout the structure. When we're looking at resonance, neither of these actually exist. It's always a conglomerate of them, right? And so it's almost like mixing two colors together. You mix red and blue, you get purple. One might be more predominant. The one that has the fewer formal charges would be more stable. So then if we're mixing to get purple, if your red structure is more stable, then it looks more like a red violet versus a blue violet. So resonance structures in the carbonate ion, we can shift the double bond around to the different oxygen atoms. And we will note then that the oxygen that has the double bond with just the 2 lone pairs has a formal charge of 0. In each of these structures, carbon has a formal charge of 0. And then the oxygen atoms that have a single bond but 3 lone pairs will have a charge of -1. And when you look at structures, you can kind of cheat in a way in terms of calculating formal charges, because we know that oxygen has 6 valence electrons. It wants to make 2 bonds. And so if it has 2 bonds, it's happy. Its formal charge would be 0. Well, if it's lacking a bond but has an extra pair of electrons, it's going to be negative because it really wants to have 2. It only has 1, so it's sad. It has 1 bond. Versus if it has 2, or if it has 3 bonds, it has an extra bond. And so then in that instance, it would be positive. So you can kind of cheat in a way in looking at your group number and saying, well, how many bonds does this atom really want to make? And then going off of that. If it wants to make 2 and it has 1, it's negative. If it wants to make 2 and it has 3, it'd be positive. So in looking at the carbonate resonance structures, all of these are equivalent. Why? Because we have the same number of formal charges on the same types of atoms. So really what's happening here are these electrons, is that these electrons are getting shared throughout. No true single bond, no true double bond. So we've talked a lot about the octet rule and forming to make sure that we have 8 electrons around our elements. Well, what happens with the exceptions? So an incomplete octet means you have fewer than. So beryllium hydride, beryllium starts with 2, each hydrogen brings 1. We have a total of 4 electrons. And so that means beryllium is forming 2 single bonds. Now keep in mind here, we've got a metal to a nonmetal, but if you compare your electronegativity differences, you'll see that these atoms are most likely to share their electrons as opposed to transfer. So beryllium only ends up with 4 electrons, and it is a linear structure. Boron trifluoride, boron brings 3, each fluorine brings 7 for a total of 24. So we're going to form single bonds between boron and fluorine. And we'll notice then that boron only has 6 total electrons around it, which makes this a really good Lewis base. Nope, Lewis acid, because it can accept a pair of electrons. Lewis bases are electron pair donors. So you can form these complexes with boron. Boron does some special chemistry because of the number of valence electrons it has, and that it kind of always has this empty little space for an extra pair of electrons. So we see boron trifluoride is a trigonal planar structure. Well, we can have odd electron molecules, which are also called radicals, which means that there are not going to be pairs everywhere. Nitrogen brings 5, oxygen brings 6 for a total of 11. So we see here that nitrogen only ends up with 7 electrons and oxygen does end up with its 8. You might ask yourself, well, how did we decide that nitrogen was going to be the one that had a lonely electron? And that's because oxygen is more electronegative, so it's going to pull the electrons closer to it anyways. So then we can also have an expanded octet, which means that we've got a central atom with a principal quantum number greater than 2. So third row or below. This is because those elements have empty d orbitals that they can hold those electrons, right? Orbitals are electron pockets. So sulfur has the capability of doing that. So 6 electrons for sulfur to start. Each fluorine brings 7 for 42, add them up, 48. So we're seeing here that sulfur forms single bonds with each fluorine atom. Each fluorine is going to have its octet because you have to for carbon, nitrogen, oxygen, and fluorine. And we have 48 electrons. So this is a stable structure, even though sulfur ends up with 12 valence electrons, or not 12 valence, 12 electrons around it. So the last bit of this chapter deals with bond enthalpies. So bond enthalpy is the energy that holds two atoms together. And just, right, the whole reason why reactions take place is because we're going to break bonds and we're going to make new bonds. So how much energy do you have to put in to break a bond? Well, some values are given here. There's values listed in your book. And so it's endothermic process to break a bond. It's an exothermic process to make a bond because you're becoming more stable then once you've put those atoms back together. So we have a new way of calculating enthalpy of reaction. So you're looking at adding up all the bond enthalpies of your reactants and then subtracting all of the bond enthalpies of your products, right? So we're back with that summation symbol, right? That's what that squirrely looking E is. Let me just mention something else. So we talked about bond lengths and comparing single bond, double bond, triple bond. So if you look here on the right-hand side of this table, just what's going on between two nitrogen atoms, we can see that going from a single bond to a double bond to a triple bond, we are significantly increasing the bond enthalpy. And hopefully that makes sense because you're having to break apart more bonds in order to separate those atoms. So calculating enthalpies of reaction using the bond enthalpies for the following reactions that I'm giving here in pink. So we have formaldehyde reacting with hydrochloric acid to form this new compound. So we're looking at each of our individual bonds and adding them up. So on the reactant side, in the formaldehyde, the H2C double bond O, I've got 2 carbon to hydrogen single bonds. I've got 1 carbon oxygen double bond. And I have 1 hydrogen to chlorine single bond. So then I'm going to subtract my product, all of those bonds. So I have an H3C there. That means I have 3 single bonds between carbon and hydrogen. I have a single bond between carbon and oxygen, and a single bond between oxygen and chlorine. So now what do I do? And this one is different, right? Because we're doing reactants minus products. So I simply look back at the table, I copy down those values, I multiply, I add, and then I subtract. So the enthalpy of reaction for this particular top reaction is 256 kilojoules per mole. So that tells us it's endothermic, and it wouldn't really be favored to happen, right? The product it doesn't want to form with all the energy that you have to put in, so the reactants are more stable thermodynamically. So if we want to react hydrogen peroxide with carbon monoxide to form hydrogen and carbon dioxide, so the second equation here, what bonds do we have to break? Well, you have to draw out your Lewis structures to see how things are connected. Hydrogen peroxide has 2 single O to H bonds and 1 single O to O bond. Carbon monoxide is a triple bond. There are 2 of them, so I have to break that triple bond twice. Then I'm going to subtract my products, which is a single bonded hydrogen to hydrogen. And then in carbon dioxide, carbon has 2 double bonds to oxygen. So there's a total of 4 because I have 2 carbon dioxides, right? So each carbon dioxide has 2 double bonded carbon to oxygens, which gives me 4. I look at my table, I plug in my values, I multiply, add everything up for my reactants, add everything up for my products, I subtract my products from my reactants. So here this shows that the enthalpy of reaction is negative 416 kilojoules per mole. So this is exothermic. So this reaction is favorable, and just thermodynamically speaking, hydrogen peroxide is not very stable. It tends to decompose anyways. It's very sensitive to light. You'll get oxygen and water, which is why hydrogen peroxide is always in a brown bottle. And carbon monoxide, to have that triple bond between carbon and oxygen, is not very stable either. When we look at the product side, we form hydrogen as a gas, which is extremely stable, as well as carbon dioxide.